Our journey begins with plate 1, the exterior hull and temporal modulation layer. This outermost shell integrates a graphene metasurface skin with a temporal modulation band, visualized in a natural dark sky setting. The lenticular layering reveals dynamic wavefront propagation, glowing mathematical overlays, and the interplay of field forces around the craft. This layer is responsible for femtosecond conductivity modulation, time inversion mechanics, and the generation of recoil-free thrust. It's the first line of interaction between the craft and its environment, setting the tone for the entire Omega Prime system. Beneath the graphene skin lies the temporal modulation layer, visualized as glowing blue-violet wave fronts that propagate asymmetrically. This layer implements time inversion and tapering mechanics, described by the operator T-EAT equals E minus night. By manipulating the directionality of electromagnetic fields in time, the system generates momentum asymmetry, as captured by the equation del-tap is proportional to integral 1.E.E. squared. 1 sive 1 dot e t 1 dot e 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 dot e. This mechanism is at the heart of recoil-free thrust and ambient energy routing, enabling the craft to harvest energy from its environment while minimizing detectable emissions. The lenticular layering of plate 1 is more than just a visual flourish. It's a functional design that reveals different physical phenomena at varying viewing angles. As you shift perspective, field equations and wavefronts emerge, much like a holographic heads-up display. This cinematic effect not only enhances the craft's visual depth, but also provides real-time feedback on field dynamics and energy routing. The result is a propulsion shell that is as informative as it is beautiful, blending science and art in a single, seamless interface. Moving inward, plate 2 reveals the magnetic lattice and phononic core. This laboratory cutaway view showcases the energetic backbone of the propulsion system, where YIG magnonic lattices and acoustic metamaterial cores work in concert. The visualization highlights the flow of EM, magnon, phonon, and lensing fields through the core, with glowing overlays and precise labeling. This internal stack is where energy is transferred, vibrations are isolated, and stealth is enhanced. Surrounding the magnetic lattice is the acoustic metamaterial core, visualized as a honeycomb porous structure with embedded electro-rheological fluid actuators. This core provides adaptive stiffness and vibration damping, described by the equation KT equals K01 plus alpha theta TT niS T0, where alpha is the modulation amplitude and theta is the heaviside step function. The result is a subsystem that isolates vibrational noise, enhances stealth, and supports high-G maneuvering, making it indispensable for advanced propulsion. The internal architecture orchestrates a seamless transfer of energy across domains. Electromagnetic waves excite surface plasmons, which couple to magnons in the YIG lattice. These magnons then transfer energy to phonons in the acoustic core. This multi-domain routing ensures recoil-free propulsion and efficient ambient energy harvesting. Temporal scrambling mechanisms further reduce emissions, suppressing detection signatures and enhancing operational stealth. Temporal scrambling is a key stealth mechanism within the phononic core. By introducing asymmetric time reflection, the system scrambles the wave history of outgoing emissions, making the craft harder to detect. This process not only reduces the craft's signature by up to 50%, but also ensures that energy is routed efficiently, supporting both propulsion and stealth in a single, integrated subsystem. Plate 2's subsystem metrics highlight its technical prowess. Magnon coupling strength is high thanks to the YIG lattice's near-zero resistance. Vibration isolation is adaptive, enabled by electro-rheological fluids. Signature suppression reaches up to 50% via temporal scrambling, while energy transfer efficiency remains high across domains. The system operates reliably from 9200 degrees Celsius to 1000 degrees Celsius, underscoring its extreme durability and versatility. The principles of magnon-phonon coupling, adaptive damping, and temporal scrambling in plate 2 are all credited to Colonel James Edward Hartman. His CHRONOAETHER-Ω framework laid the groundwork for these innovations, which now form the energetic engine of the Omega Prime propulsion system. Plate 2 bridges the outer modulation shell with the resonant geometry and lensing interface, ensuring seamless integration across all layers. Plate 3 introduces the Fibonacci hull geometry, visualized as a holographic spiral cavity overlay. This design reveals golden ratio spiral arms expanding outward from the craft's center, with concentric resonant cavities spaced according to the Fibonacci sequence. Temporal modulation bands align with cavity nodes, optimizing resonance and minimizing wave losses. This spatial logic is key to the craft's stealth, energy routing, and field shaping capabilities. The golden ratio spiral is a hallmark of efficient natural design, and here it's applied to optimize the hull's resonance properties. The Fibonacci sequence determines the spacing of resonant cavities, with each radius given by Rn equals R0 sim, where 0 is approximately equal to 1.618. This quasi-aperiodic spacing minimizes wave losses and enhances temporal cavity resonance, supporting both stealth and energy efficiency. The omega 80 prime correction refines the Fibonacci geometry by introducing a temporal cavity drift term, omega. The corrected radius formula, Rn equals R0 Ui0 plus minus omega, accounts for dynamic shifts in the temporal domain, ensuring that resonance remains optimal even as the craft's operating conditions change. This adaptability is crucial for maintaining stealth and performance in diverse environments. By aligning temporal modulation bands with the nodes of resonant cavities, the system maximizes energy retention and minimizes scattering. This optimization not only enhances the craft's stealth profile, but also supports efficient field shaping and energy routing. The result is a hull that is both structurally elegant and functionally advanced, embodying the best of natural and engineered design. The Fibonacci hull geometry delivers measurable benefits. Wave losses are minimized, temporal cavity resonance is enhanced, and stealth capabilities are improved through quasi-aperiodic spacing. The system's adaptability ensures optimal performance across a range of operational scenarios, making it a cornerstone of the omega prime propulsion architecture. The application of Fibonacci geometry and temporal modulation in Plate 3 is a direct result of Cole-Hartman's vision for multi-domain adaptability. By merging natural mathematical patterns with engineered precision, the omega prime system achieves a level of stealth and efficiency unmatched by conventional designs. Plate 3 stands as a testament to the power of interdisciplinary innovation. Plate 4 brings us to the temporal lensing in 4D interface, visualized as a blueprint-style schematic. Here, bent wavefronts refract through the temporal interface, guided by the generalized Snell's law and omega UA prime curvature equation. This interface is where field steering, stealth, and multi-domain adaptability converge, enabling the craft to operate seamlessly across air, water, and vacuum. The temporal lensing interface is governed by a generalized form of Snell's law, adapted for omega dot prime physics. The equation n1 sin theta 1 c1 equals n2 sin theta 2 c2 plus delta con. Cotton introduces a temporal offset and refractive index gradient, allowing for dynamic control of wavefront refraction. This enables the craft to steer energy precisely, supporting both stealth and propulsion. Lens curvature at the temporal interface is defined by the omega UHEY equation. Kapot equals CWO WT WOEN, CWO T squared, 1 plus CWO N CWO squared. This formula determines the optimal shape for field routing, ensuring that wavefronts bend precisely as needed for stealth and propulsion control. By dynamically adjusting curvature, the system maintains high field steering precision across all domains. Bent wavefronts at the temporal interface allow the craft to steer energy across multiple domains. By modulating the refractive index in real time, the system can redirect fields for stealth, propulsion, or adaptive control. This capability is essential for seamless operation in air, water, or vacuum, giving the omega prime craft unmatched versatility. Temporal lensing not only enables precise field steering, but also enhances stealth by minimizing scattering and maximizing asymmetry. The dynamic modulation of the refractive index creates routing paths that adapt to changing operational needs, ensuring that the craft remains undetectable and efficient in any environment. The geometry of the temporal interface is carefully engineered for smooth hull curvature, aligned with Snell interface angles. This design minimizes scattering and maximizes field asymmetry, supporting both stealth and directional thrust. The blueprint-style schematic highlights these geometric relationships, making the underlying physics visually intuitive. Plate 4 subsystem metrics reflect its advanced capabilities. Field steering precision is high thanks to Snell gradient and curvature control. Stealth capability is enhanced via temporal scrambling and wave redirection. The system transitions seamlessly across air, water, and vacuum, with temporal refraction tunable via deltat and Sohn-Cott gradients. Real-time modulation of lensing geometry ensures optimal control at all times. The temporal lensing principles in Plate 4, Snell interface extension, curvature shaping, and field steering are all rooted in Colonel Hartmann's CHRONOAETHER-Ω framework. This final plate completes the Chapter 1 series, establishing the full outer-to-core architecture of the CHRONOAETHER-Ω prime craft. It sets the stage for deeper explorations in subsequent chapters. The Ω prime edition introduces an enhanced mathematical suite that underpins the entire propulsion architecture. Key equations include temporal lens curvature, generalized Snell's law, momentum asymmetry, and Fibonacci omega resonator geometry. Each formula is carefully integrated into the system's design, ensuring that every physical layer is mathematically optimized for performance and adaptability. Temporal lens curvature is a critical parameter for field steering and energy routing. The equation CAPAT equals FUE2L quart in, COT squared 1 plus COT, FUE quad, defines how the refractive index evolves over time, shaping the lens for optimal performance. This mathematical insight allows the Ω prime system to dynamically adapt its field interfaces, maintaining efficiency and stealth in real time. The Ω prime Snell law extends classical refraction to include synthetic frequency dimensions and temporal gradients. The equation N1 sin theta 1 C1 equals N2 sin theta 2 C2 plus delta psi 4 plus omega psi introduces a correction term, omega psi, accounting for the effects of frequency domain stacking. This allows the system to achieve multi-harmonic propulsion asymmetry, a key advantage of the Ω prime framework. Momentum asymmetry is fundamental to recoil-free propulsion. The Ω prime form, deltap equals integral, ninth, psi, tide, ninths, psi, u eds, tower, ninths, psi, tower, ninths, tower, tire, plus integral omega psi tdt captures the difference in energy flow between time-forward and time-inverted fields with an added correction for synthetic frequency effects. This equation is implemented at multiple layers of the system, ensuring efficient thrust and energy harvesting. The Fibonacci omega resonator geometry is central to the system's spatial logic. The formula Rn equals R0y sim plus mine omega defines the radii of resonant cavities, incorporating both the golden ratio and a correction for temporal drift. This ensures that resonance conditions remain optimal, supporting stealth and energy efficiency even as operational parameters shift. A defining feature of the Ω prime system is its ability to route energy across multiple domains: electromagnetic, magnetic, phononic, and etheric. Each layer is optimized for minimal loss and maximal adaptability, ensuring that the craft can operate efficiently in any environment. This multi-domain routing is visualized through layered field overlays and dynamic field lines. The Ω prime framework is designed to extract energy from ambient sources, including urban RF, atmospheric turbulence, and gravitational gradients. Specialized rectification layers capture and convert this energy, supporting both propulsion and onboard systems. This capability enhances the craft's operational endurance and reduces its reliance on conventional power sources. Temporal cloaking is achieved through specialized Ω prime layers and entropy scrambling. By time-shifting emissions and scrambling wave histories, the system masks its operational signature, making detection extremely difficult. This advanced cloaking is a direct result of the system's mastery over temporal modulation and field asymmetry. The Ω prime system supports high G maneuvers through inertial cancellation and recoil-free thrust. By dynamically adjusting field interfaces and leveraging time-inverted wavefronts, the craft can accelerate rapidly without subjecting its occupants to extreme forces. This capability is essential for advanced maneuverability and mission flexibility. Operating in relativistic regimes, the Omega Prime craft manages time, dilation effects, and delta accumulation. The system's temporal modulation layers create safe operation envelopes, ensuring that both the craft and its occupants remain protected during high-speed travel. This advanced control over relativistic effects is a testament to the framework's mathematical rigor. The Omega Prime propulsion system is domain agnostic, enabling integration with UAP-class vehicles that operate in air, water, vacuum, and plasma. Its multi-domain adaptability and field steering capabilities make it suitable for a wide range of craft, from atmospheric flyers to deep space explorers. The culmination of Chapter 1 is the full system blueprint, a cinematic, multi-layer 4K cutaway that integrates all subsystems. This master diagram reveals the interplay between exterior hull, internal lattice, resonant geometry, and temporal lensing. Each layer is labeled with its key equations and field interactions, providing a comprehensive overview of the Omega Prime propulsion architecture. Every innovation in the CHRONOAETHER-Ω Omega Prime framework is credited to Colonel James Edward Hartman, whose vision and research have redefined the boundaries of propulsion science. The Chapter 1 series stands as a legacy artifact, blending technical rigor with cinematic storytelling. As we move forward, the groundwork laid here will support even deeper explorations into synthetic frequency dimensions and multi-harmonic propulsion. With Chapter 1 complete, the stage is set for the next phase, exploring synthetic frequency dimensions, harmonic stacking, and multi-frequency propulsion asymmetry in Chapter 2. Each new chapter will build on the cinematic and technical foundation established here, continuing the journey through the most advanced propulsion architecture ever conceived.